Ya se está viendo, ¿no? Vale, perfecto. El email que te mande lo metes aquí, ¿no? Pues muchas gracias. Cuando me digáis ya... Cuando tú quieras. Okay. Hello, good morning. Thanks to all of you for coming. So it's my pleasure to start this series of seminars El Almendro. For those of you who doesn't know, I guess that everybody that is following probably speaks Spanish, but anyway, I will just keep practicing my English. So for those of you who are not like born or grown in the Spanish culture, there was like a famous commercial for turrón, you know, good Spanish turrón, very popular several years ago, that was called El Almendro, vuelve a casa por Navidad, something like the almond tree, come back home for Christmas. So the idea is that, you know, when Christmas comes, a lot of people from abroad comes back to the origin, and this is what many Spanish researchers actually do. So when they come for vacation to Spain, since we are in the capital city, many of them, they have to stop by Madrid because, you know, all the connections basically pass through Madrid. So the idea that came up between Álvaro and me, like I guess it was last year, right, Since we normally get together and talk and go for beers and all these sort of things, why not doing this a little bit more formal? So we could actually get together, give some seminars, and besides the fact that we are all friends and we like to get together and talk about science and other stuff, of course, it is also the fact that I think it's nice that everybody is somewhat connected, so we can know what other people is doing, and we can know that there is a lot of world out there. So it's not only Spain, the only place where you can do science. There are good Spanish scientists that are all over the place, and that they are very happy to come back and to give seminars and these sort of things, right? So this is the idea of these seminars. This is the first edition. I hope that everything goes well enough to continue this thing in the future years. And, well, actually, the idea, as I said, it was that everybody from abroad, or let's say that everybody that talked was from abroad, but somebody told me, like, you know, you are the organizer, you should, like, get a little bit more involved and say something. So I'm going to talk about the last thing, or the latest, actually, that I have presented in a conference, which is this problem of the beer bottle. So I'm the first speaker, right? I have to introduce myself. I'm Javier Rodríguez. I studied aerospace engineering at the Polytechnic University, and then I did my PhD here in Carlos III. I went then to San Diego for a postdoc for 2 years, and then I came back here where I somehow I became professor or associate professor, and this is like my trajectory, right? So let me start with my presentation today. My presentation is about a very popular problem that it's called the beer tapping. Beer tapping, I wanted to have a couple of beers, but I forgot to get them. So this beer tapping thing is this phenomenon that happens when you tap, you hit the mouth of a bottle, right, with another bottle, and what you see is sort of this. Oh, I forgot, I made one question. Is it okay if I put this here? ¿Puedo poner esto aquí? Sí, okay. This is kind of risky. All the cables that the presentation depends on are now moving, all the connections. So this is to prove the robustness of the connectors. Okay, test check. So this is the beer tapping phenomenon, right? This thing here, this is what you guys can see that happens in a bar. So you open your bottle of beer in a bar, and then somebody that pretends to be your friend then hits your bottle typically with another bottle, right? So you can see that within a few seconds, actually I'd say in a time of about 1 second, you see that most of the beer that you just paid suddenly becomes or turns into foam, right? In fact, this movie is like slowed down a little bit, so this is acquired like at 120 frames per second and played at 30, so it means that it's like slowed down by a factor of 4 or something like that. But this is pretty much what happens. So you can see, let me see if I can see that again, right? So initially the bottle is hit, and then you see that these beautiful columns of foam start to develop. What is quite remarkable of this phenomenon is that these clouds of foam, they grow very, very fast. So this is the thing that we were, one day actually we were in a bar, and we were wondering why this thing happened. And then we started to put together some attempts of explanations. Neither of those explanations was convincing enough, so we decided to take the thing to the lab and do properly done experiments under well-controlled conditions and so on and so forth. So this is what we did. So we took a bottle to the lab. We didn't do these kind of things there because this is not a controlled experiment. Instead, what we did, as you can read here, right, we first of all kept the bottle fixed. Then we put together a system to drop weights in a very controlled and repeatable way, so we can guarantee that all the impacts are exactly the same. And then, as this is the way of exciting this beer tapping phenomenon, then what we did was to measure what happens inside the bottle using basically 2 techniques. One of them is to measure the pressure with a hydrophone, so we can see how is the pressure wave field that is developing inside the bottle. And the other thing is to record, to see what happens with the bubbles inside the beer with a high-speed camera. So this is essentially the experimental techniques that we have used. And then I'm not going to talk now about the production of bubbles, but you'll see that the way in which we produce the bubbles is also kind of interesting. This is a very beautiful part of the experiment. So this is what we did, and this is the explanation of why the foaming over occurs when the bottle is tapped. So we have divided the process in different stages, attending to the physics that rules or dominates each stage, and of course, you'll see the duration of each stage. So the first stage is what we call the wave propagation stage. What happens there is kind of easy to picture. So you have your bottle, you hit the mouth of the bottle, and then immediately you trigger a compression wave that travels downward through the glass, okay? This compression wave gets to the bottom of the glass, and what happen, or the bottle, and what happens when a compression wave meets a free end boundary condition? That this compression wave bounces back as an expansion wave, right? For those of you that are not like in the engineering, mathematics, physics world, if there is any, let me tell you that this is very similar to what happened with a spring. So you compress a spring, you release the spring, right? And then the spring immediately expands, right? And then it compresses back again. So this is similarly, kind of similar to what happened to the bottle, right? Of course, the interesting point here is that the bottle is not alone. In fact, the bottle is connected to the liquid through the bottom, meaning that when you move the bottom of the bottle, the liquid has to follow that bottom, right? So it means, these are not the compression waves. So it means that when the compression wave reaches the bottom of the bottle, there is an expansion wave that travels, but this time through the liquid. So you can imagine that the liquid at that stage is stretched, is expanding, right? What happens then is that the small the small gas cavities, CO2 cavities that are inside the beer, since we are reducing the pressure, these cavities are going to grow, right? We'll see that thing later. Anyway, when the wave gets back to the free surface, the wave bounces back as a compression wave, right? Then it comes back to the bottom, and then it bounces several more times. So this is basically the kind of pressure field that we are going to find. To prove this thing, to prove that this is not just one idea, this is something that we can measure, we plot there at the right the measurements acquired with a hydrophone. So there you see lower than 0 means expansion, so tension, and greater than 0 means compression. So B is the stage when the rarefaction or expansion wave goes through the liquid, and then the C is the stage where the compression wave passes through the liquid. So you'll see that as we expected, we have this series of can you guys fix this, please? Thank you. So you can see that there is this expansion stages, the B stages, followed by these compression stages or C stages, okay? So this is, as we said, this is this train of expansion compression waves traveling through the liquid. Now, what happens with the bubbles? I anticipated a little bit, but now we are going to see that much better. As I said, when the expansion wave travels through the liquid, as you can see in this high-speed movie, what happens is that the bubbles are going to grow. So this is, if you notice at the right, there is a high-speed movie there, right? You see that initially the bubbles start to grow. Where do you expect the bubbles to grow first? Obviously close to the bottom, because the expansion wave is starting from the bottom, right? So you see that the bubbles initially start they start growing close to the bottom, then this expansion wave travels upward, and you see that the bubbles keep growing, right? Following this expansion wave. Now, when the compression wave bounces back, right, you see that initially the bubbles that are close to the free surface, or that are at the upper part of the bottle, these bubbles are going to compress. Obviously, this compression that the bubbles experience, if this compression is intense enough, because the pressure wave that you have is very strong, then what happens is that the bubble is not going to be to do that in a spherically symmetrical way. So the bubble, when it compresses or is compressed very rapidly, the bubble collapses or implodes, and it means that the bubble is going to break up, because the impact is so strong that there is no way that you can keep the spherical symmetry. If you guys want to picture something similar in your mind, imagine that you try to compress a balloon, right? So you have an air balloon and you try to compress that very, very carefully with the hand, right? It's not easy, of course, but maybe you sort of can keep the spherical shape of the balloon. But imagine that you try to do that like this, like very, very fast. What happens? That the balloon is going to have these blobs, right, that try to escape between your fingers. So this is like a very crude, very simple picture of what happens here. The technical word, of course, is not compressing a balloon or anything like that. It's called Rayleigh-Taylor instability, but this is just a fancy way of describing what I just said, that when you compress something very quickly, that thing doesn't keep the spherical symmetry, okay? So this is what you will see that bubbles are going to do next. But before that, I would like to talk about the bubble generation that we have in our experiment. So if you notice, we have here a very beautiful, a very neat column of bubbles, right? In fact, typically you don't have those things in a beer bottle. So your bottle, I mean, it may have some trails of bubbles, right? But definitely not a column like this. So the reason why we have this column is because we put here, I don't know if you guys can see, we put here a metal washer, essentially, to trigger the formation of bubbles. Why? Because we want to do experiments in a controlled way. So we don't want to depend on the gas cavities that naturally occur in the beer. So we want to have our bubbles there. We want to know where the bubbles are going to be, so we can focus the high-speed camera there, and so on and so forth, right? So we produce the bubble in a relatively controlled way. But now you may ask, but this is not what happened in a beer bottle. So when you open the bottle, you typically don't put things into the bottle, right? So the thing is clean. And nevertheless, this beer tapping thing occurs. Why? Well, the explanation is because in all sort of carbonated beverages, in particular in beer, you always have these small gas cavities. Where are they? It all depends. Basically, there are like two sources. One source is in the glass. So when you have a glass, typically the glass is not perfect, right? The glass has like scratches and imperfections, and small gas cavities can get trapped into those imperfections. So you always have those things there, right? But there is even a more interesting source of these gas cavities, which are cellulose fibers. So there is this beautiful theory by Liger-Veller, and he said that when you see these trails of bubbles running through the glass of beer or champagne, essentially those things start from a cellulose fiber. And the cellulose fiber is like a tube, very thin, about a few, let's say 10 microns in diameter. And what happens is that there is like a small gas cavity, air cavity inside that cellulose fiber. So that thing acts as a source, as a seed for the nucleation, right? I must admit that I didn't believe that initially. So then what I did was to take a glass of beer to the lab and see what was at the origin of one of these beautiful bubble trails. So this is the results that I'm going to show you. This is a picture, it's not mine, of a glass of beer with the trails that I'm talking about. So they are familiar to you guys, right? So you see the kind of trails that I'm talking about. So what we did was to take one of these glasses, take that to the lab, and then use a high-speed camera to see what happens very close to the origin of one of those trails. And then what we saw was this thing. Right? This is magnified like 7 times in size, so it means that this sort of dirty line that you have at the bottom of the movie is about, I would say, 50 microns, something like that. So this, ladies and gentlemen, is what you find at the origin of these bubble trails, right, when you take them to the lab. So obviously there was something there. I mean, still I was reluctant to believe that this was a cellulose fiber. So then we said, well, how can we tell if this is a cellulose fiber? Well, scratches typically don't disappear. So let's try to move the thing and see if we can get rid of it, okay? So then we did that. We took with a pencil and tried to move this supposedly scratch or whatever. And accidentally, we obtained something very beautiful, that is the movie at the right. Right? You see, obviously it's not a scratch because it's physically moving. So it means that it's something, some sort of imperfection that was there, and as you can see, acts as a nucleus, as a seed for the nucleation of bubbles. So the idea is you always have those guys in beer. Actually, in all carbonated beverages, like champagne, beer. So these cellulose fibers are everywhere, and the reason, the consequence of this is that when you hit your bottle, the liquid is never perfect. There are always a lot of gas cavities that act as nucleation sources when you impact the bottle, okay? The only problem with these guys is that you don't really know where they are, so this is not very good to do experiments. And that's the reason why in our experiments we put things to release the bubbles precisely where we want, okay? So that's the only difference. But this is like to get rid of the critics who say that this is not real because, you know, we actually put bubbles there. Bubbles are always there, okay? Now, coming back to the explanation, you remember that I stopped talking about the dynamics of this expansion, compression waves, and then I said that when the waves are very intense, they make the bubbles implode, so basically collapse, break up, and lose symmetry. So this is a movie that we took in the lab, right, of what happens with the bubbles, right? Can you tell that obviously they start oscillating, and at some point they lose the symmetry, they break up, and we no longer have bubbles. What we have instead are, let me see if I can play that again. Right? It's not easy to control, eh? Let me see if I can. Okay, here it is. Can you see the bubble, this one there, the biggest one that you can tell, right? So you see that that bubble is no longer a bubble. Now it's actually a cloud of foam, because this bubble, this initial bubble, broke up, right, due to this Rayleigh-Taylor instability, and then you no longer have a bubble. You actually have this foamy cloud of tiny bubbles, right, that are like very, very small. I know that this is not the right way of seeing the thing, so let me magnify the movie, right, so you can not only see the bubble magnified. Sorry, 1 second. I'm not very good with PowerPoint, right? Okay, so this is the same bubble with the radius, right? Can you tell what happened now? So the bubble expands. As a result of this expansion wave, the bubble collapses very rapidly. This bubble is kind of lucky because it doesn't break at the first implosion or at the first compression, but then it can't withstand the second one. So after the second collapse, what happens is that the bubble breaks up. And then, as I said, you no longer have a bubble. You have a cloud of foam, right, in which essentially, and this is the key idea, one of the key ideas, essentially you have the same volume right after the implosion, but instead of having only one bubble, you have like about thousands or hundreds of them. What is the result? That you have the same volume, but the interfacial area between the gas and the liquid is far larger. It's much, much larger. It's typically of the order of the number of fragments raised to 1/3 times larger, right? So this means that you have enhanced it very much a process known as diffusion, right? So essentially diffusion is the process responsible for the gas in your beer. So when you have a beer bottle and you leave it open on the table and then you come back the next day, right? That happens a lot when you live alone. Then you find that the beer is basically free of gas. There is no more gas there, right? We say in Spanish, pierde la fuerza, no? So loses the strength. So this is diffusion. What happened in that process is that the CO2 that is dissolved in the liquid very slowly through diffusion, which is a slow process, goes to the free surface of the beer, and then this gas just dissolves into the atmosphere. So about a time of the order of 1 day, your beer no longer has gas. Obviously, the process is the same here, but the big difference is that instead of the gas having to make all the way to the free surface and then evaporate there, right, what happened is that now we have a lot of gas cavities, small gas cavities, with a lot of surface area respect to the volume that they have. So in few words, we have made the process of diffusion very, very efficient. So now what we see is there is a stage that lasts typically, as you can see in the plot in the right bottom corner. This process lasts in the order of a few tenths of milliseconds, and during those tenths of milliseconds, the size of the cloud, you see that it increases by a factor of about 2 point something, 3. Keep in mind that this is length. So if we want to know what happens with the volume, you have to cube that thing. So it means that in about 10 milliseconds, the cloud of bubbles, the cloud of foam, increases, grows by a factor of the volume, by a factor of about 10, which is a lot, right? So essentially, this state is not very long, as you can tell, because very rapidly the growth is so fast that the bubble runs out of CO2, so there is a depletion of CO2, right? So the guy doesn't grow anymore, but that's all enough already. So we have put in very short time a lot of volume there. So what happens when you have a liquid or air, for what matters, and you release suddenly like something very hot, something that is much lighter than the environment? Imagine an explosion, a nuclear explosion. What happened? Well, you put there a lot of energy, so the temperature rises a lot, so the density decreases a lot, so buoyancy acts because the pocket that you have there is much lighter than the surroundings, so therefore you create a mushroom. You create one of these mushrooms that you see in the explosion, right? Exactly, this is the same thing that is going to happen here. So these are at the leftmost frame, you see the bubbles before the implosion. At the central frame, you see the bubbles right after the implosion. And at the right, you see what happened, I guess it's about 100 milliseconds later. And then you see these tiny mushrooms, these tiny explosions, if you want, right, that resemble very much, albeit in a much smaller size, of course, these nuclear mushrooms or these sort of explosive mushrooms that you see in explosions on TV. So these are some frames. At the right, you have a much better control experiment in which we have an isolated bubble that does this thing, right? So you see how, in fact, wait until it comes back. Here it is. Bubble explodes here. It grows a little bit, and then you see how it develops this mushroom, this explosion. Okay. Now, this stage that we are now talking about is by far the most efficient one in terms of releasing volume. So when you see how much gas you are releasing, how much CO2 you are taking out of the liquid and back into the gas form due to the different stages, this is by far the most efficient. And the way of seeing that is by measuring. So we not only have these movies because they are beautiful and we can play them in conferences, we can also measure things in these images. And in particular, in the sort of images that you have there, we have measured the height, the distance that it has traveled. I will talk about that later. But more importantly, we can see this plot here, the lower plot, in which you can tell the different stages. You see the initial growth, right? which is, has a slope of the order of 1/2 in a log-log plot. This is just a confirmation that is driven by diffusion, okay? So you have this diffusion stage, then you have this depletion stage in which the thing doesn't grow anymore because the CO2 is depleted, and then notice how fast the growth is in the third stage, in this buoyancy-driven stage. I didn't plot that thing there, but we have measured that the size of the cloud grows as the square of the time. So it grows like very, very much, right? So this buoyancy-driven stage, as you can tell, is by far the most efficient. I mean, it might not look so impressive when you look at that, but keep in mind that this is a log-log plot. So it means that you are gaining volume by a huge factor when you are in this buoyancy-driven stage, okay? So this is the whole picture of the problem. You have this diffusion-driven stage, right? The bubble cloud grows as this T to 1/2, depletion, and then buoyancy takes over, and then the thing is really explosive, and it grows so fast, okay? One thing that we did later on, when you take a look at that figure, you say, well, you can tell that this grows as T raised to 1/2, but there is a lot of noise, right? So you actually, you can, being optimistic, you can fit many different power laws to that curve. And the reason why we have that noise is actually not because it is noise. It's not like experimental noise. The reason is because right after the bubble cloud starts to grow, right, the waves, these expansion compression waves, they are slowly damping out, but still they are there. So it means that this bubble cloud, when you look at the movie very carefully, you see that it breathes, right? It inflates and contracts a little bit. So this is the reason for all the scatter that you see in this figure. It's not really experimental error, it's something that is there. Anyway, we don't want that thing because it's not so clear that that thing grows as the time raised to 1/2. So then we needed to come up with a different way of producing the same phenomenon, but without the waves, right? So we could see the thing growing by diffusion. So then we came up with this interesting idea, which is something that everybody wants to do, which is to shoot a high-powered laser pulse into the beer, right? Let me go back, right? Notice that we have a convergent lens there, right? And you see that at time 0, we shoot high-powered laser pulse with a convergent lens, as I said, to the beer. What is what you see? Exactly the same thing. So you see this mushroom, you see this bubble cloud that grows, and that's exactly the same thing as if you had a bubble that was exploding or imploding, in fact, due to these compression waves. So this is very cool, not only because, the experiment is cool itself, this is very cool because when you analyze the size, how this plume grows, this laser-induced plume grows, when you see that, right, is the red curve here, you see that, in fact, it does the same thing. So it has these 3 stages, right? And more importantly, at short times, when you have this diffusion-driven stage, now since there are no these trains of waves, then you see that the thing grows as the time raised to 1/2, very smoothly, very nicely, in fact proving that this diffusion-driven stage is in fact driven by diffusion, okay? So this is essentially the phenomenon. Just one more interesting comment. So you may ask, why is this buoyancy-driven stage so efficient? So what makes this guy so efficient in terms of degassing the liquid, right? Well, the idea is that these plumes, they are autocatalytic. Autocatalytic is a fancy way of saying that the faster it moves, the faster it grows, and the other way around, right? So in fact, the reason, well, there could be several reasons. This is where now we are doing the research, but it's kind of obvious from what we know right now that when the cloud of bubbles grows, right, as it grows, it changes the shape, it mixes the inner liquid with the outer liquid, right? So it means that it takes fresh CO2 from out there, from out the vortex ring, from out the plume, and then takes or mixes that CO2 into the plume, right? So that's one effect that probably is occurring there. But there is a second effect, which is the effect of advection. So when you have an individual tiny bubble rising, right, this bubble rises very slowly. So it means that it moves through regions of fresh CO2 very slowly, right? However, when you have a cloud of bubbles, the buoyancy of all these bubbles acts together, and then you have a rising motion, a buoyancy-driven rising motion that is a collective motion. So it's like the buoyancy of all these guys adds up, and therefore this thing rises very fast. So probably these two effects are together, and this is the reason why the thing is autocatalytic, meaning that it grows faster the faster it rises, and the other way around. But the thing is that at this point we cannot tell which effect is dominating. These are the experiments that we are doing right now. Anyway, the thing grows faster than it would grow if you just put there a fixed amount of heat and let it go, right? And one proof that this is the case is that it's kind of well established that when you have a thermal, right, like you release some, as I said, some explosion, right, the plume that you create, the mushroom that you create, the velocity goes as the square root of the time, right? Sorry, it decays as the square root of the time. So initially it moves very fast, but then the velocity quickly decays. And here we don't see that thing. So if you see the upper plot, you can tell this is actually the position of the top of the mushroom, right? You see that the guy pretty much follows a constant velocity. So this is a proof that the process is autocatalytic. It's not just because you release some buoyancy and then it rises. No, no, no. It's all the time the thing keeps releasing, keeps generating buoyancy, okay? So this is the physics that we have understood so far. And since we want to go further and understand more things, we are considering, or we are starting to do preliminary numerical simulation, right? So we are doing numerical simulations using Jerry's, and one of the goals that we have with these simulations is to compare what an individual bubble does compared to the cloud of bubbles. So here we plot at the left, we have the red curve, is the size, well, the volume actually of an individual bubble, right? Now, imagine that you take one of these bubbles, and instead of having one, you have a cloud. So you put many of them together, as we do in the right panel. What happens? That you can measure how is the average volume of one of these bubbles belonging to the cloud as a function of time, and then you get the blue curve. So you see, in fact, how initially they do exactly the same thing. They grow equally fast. Then, when you are in the cloud, you have this depletion stage. You can tell that the blue curve sort of achieves or reaches an asymptote, right? And then acts the buoyancy, and then what you have is this very, very fast, very, very rapid growth that you can tell there, okay? So this is a preliminary numerical simulation. By preliminary, we mean that the physics that we have put in the model is still not the full one, because we don't know that physics. We are investigating that. But it's kind of clear at this point that obviously this collective effect of rising is very important to promote the explosive the explosive growth of the bubbles, okay? So these are the main conclusions, and now this, just as a summary, this is what we have learned from this experiment. That is very complex. It's not something that you can explain in about in one night, so you have to do things in the lab, right? And then basically, it's very nice because you can see a lot of physics in there. I wouldn't say that all the classical physics is here, but I would say like 80% of the classical physics that you study in a school of engineering is in this problem. So you have like compression and expansion waves, right? Elastic waves propagating through the solid, elastic waves or sound waves propagating through the liquid. You have diffusion, you have the transport of diffusion, right? Moving or making the bubbles grow. Then you have this buoyancy-driven stage in which you have these mushrooms that grow explosively and so on and so forth. And finally, I mean, there may be other effects that are not like central to this problem, and therefore we don't discuss. But something that I would like to point out is that something that initially started as a prank in a bar, so something that we studied just for the fun of it, eventually covers so many topics of physics that is very, very hard not to find applications. So when people ask what are the applications for this, I mean, probably many more that we can tell. So my advice to finish this is be curious, because you don't know whether you're going to find a very nice, very beautiful problem with a lot of physics inside, okay? So thank you very much for your attention. Let me finish with this. If there is any question, I guess. Yeah, this is the movie I want to be playing. So questions, online or physically here? No? Really? I guess so. I mean, the thing is that if somebody is following us, which I don't know.
Yeah, I'm sorry to have a microphone because it's a pretty stupid question. I'm not sure if I follow right. So here, normally what you have with the beer tapping, you tap the beer and then you have a wave that is coming up and down. This, as I understood.
Liquid, right.
And the experiments you're doing also. Was it a piezo? I missed the point. You had a piezo, like sending the waves, or in the control experiment?
No, in the control experiment it's not a piezo. What we have is a bottle. The bottle is grabbed in a way with a flexible support, So the wave is not killed due to the support, but
Okay.
the bottle is not allowed to move. Because if the bottle moves, then people kind of say, you know, a lot of things could be happening here. So we want to have the experiment as clean as possible, meaning that the bottle is fixed, but the support is sort of flexible, so the wave can go through. Okay? And then what we do is the more realistic situation compatible with having control conditions, which is just to have a weight, a brass weight, in fact, of 90 grams, 180 grams, different weights, and then we drop them from different heights. And then the cool thing is that we have a rail, so the weight doesn't really drop. I mean, it drops, but it goes guided through a rail. So it means that the impact is exactly the same always. So, but we actually do impacts. We don't have a piezoelectric system like insonating, right, or pulling or compressing the thing.
And then the key point is that you have several cycles of compression and dilation of the bubbles. And how many do you have before? I mean, because I guess this is, I mean, the amplitude of the wave goes down really fast, no?
Really fast, yeah, exactly. I mean, I just plot here in this figure, there. I just plot here like 1, 2, 3 periods because I want to see the thing. But if I mean, I want you guys to see how it's the oscillation. Sure. But notice that even during these 4 periods, the amplitude starts to decay. So if you look further in time, you'll see that the thing goes on, and the amplitude decays slowly. But it decays, of course. So, and this is natural. I mean, the same thing, I guess, happens in the beer bottle.
So then, within a few cycles, you already have the foam created. Then.
Well, typically, bubbles don't take more than 1 or 2 compression cycles. So that's a very good thing, because even if the experiments are as controlled as we could, there is some technicalities, right? In fact, when you drop the thing, it typically bounces back. So when you drop the weight, the weight bounces back again, and there is a second impact, typically like after 3-4 milliseconds, right? Fortunately, that is like very, very long compared to the time taken by the bubbles to implode. So notice, I didn't mention that, but if you see the time scales of these waves, they are tiny. So we are talking about the first cycle of expansion compression occurs in about 0.2 milliseconds. 200 microseconds, right? So it means that by the time that bubbles implode and turn into foam, nothing else has happened. So from that point of view, you have like a pure expansion compression and no effect of the damping or anything like that. However, when you have these bubble clouds that start to grow and they take like tens of milliseconds to grow, the thing is different, because during that time other expansion compressions can affect the growth. And that's the reason why you see this guy growing in such a distorted way, like here, right? You see that there is a lot of noise. It's not noise, it's actually there. It's not an experimental noise, it's the physics. But you see that the growth is not clean. It's like it oscillates around T to 1/2, but it's not like purely following the thing as the laser-driven implosion does.
Thank you.
Thank you. More questions? Okay. So don't get rid of that because you are the next, I guess. So it's my pleasure to introduce our next speaker, which is, there is a thing I should have told you. You need to plug your presentation here. Is that possible? No, to plug, I guess, to copy the presentation here.
Yes, I can, yeah.
Okay, so then we have like a 5 minutes break because I guess it will take some time for us to copy the thing.